let's solve this one. A hard closest room, 2100 rated problem. There is a hotel with n rooms. The rooms are represented by a 2D integer array. So we get pairs with a room ID and the size of the room. The room IDs are unique. And we also get queries which include a preferred and a minimum size. And we want to find a room for each query at least of size at least mean size, and we want to find the closest ID to the preferred ID. There is a tie. In the absolute difference, we use the room with the smallest such ID. There's no such room. The answer is -1. Okay. So here in the second query, the minimum size is 3, and there are no rooms of 3 or more. That's why we have to return a -1 in that case. And there are up to 10 to the 5 rooms and 10 to the 4 queries. So I wanted to solve this problem because it illustrates a very useful technique, a couple of useful techniques. So the first observation here is that we have 2 conditions for our query. One is a bound condition. It is a strict condition because we only want to consider the elements of size greater than or equal the value of the query, the mean size. But then the second criteria is in terms of distance. So we can handle these 2 conditions separately. For the mean size condition, there is a trick. I think this technique I used this technique to solve a Q4 in a recent LeetCode contest. So if we process the rooms and the queries from higher to lower size, we can make sure that when we process a query, we have already processed all the rooms that have size greater than or equal the mean size of our current query. And maybe we can add those rooms into a data structure, and we only need to apply the second criteria to that set. So by sorting and by processing them in this order, we handle the mean size criteria. And now for the second criteria, we can use a data structure that can give us the closest element for a given value. Because I mean, the absolute difference is another way of saying distance. So we want the closest value in the set to a given, to the preferred value. So in Python, there is a sorted list of sorted containers that provides this kind of query, which is essentially like a binary search, but since we will be adding elements to the set, that's why we need a dynamic data structure. And I think that's all we need. So let's start by sorting. Like I said, well, here, whenever you are asked to, when you want to reorder the queries, but you're asked to return them in the original order, there are a few ways you can do this. I like to create an order array of indices and sort them that way. So these are all the indices of the... Yeah, I'm back. I'm pretty active today. So we're going to sort the indices based on the mean size of the query. So this is going to be an index, and we want to consider, and the mean size is the second component, so that's why we use 1. And let's do it in reverse because we want to go from highest to lowest. So that is going to give us our order, and we can just do it this way. Then we also want to sort the rooms. I don't enjoy algorithm streams. Well, I mean, of course there is value. You don't want to spoil problems. You want to give them an honest effort trying to solve problems, because that's how you improve at problem solving. But you also want to you also, even if you solve it, you want to learn better ways to solve it, maybe better explanations. And if you couldn't solve it, it's useful to solve. Maybe you needed a new to learn a new technique. You can learn it by watching the stream. You can also watch the VOD, and you can pause it and try to solve the problem first. So yeah, I know that this content might be more might be better for video and not for live stream, because of what you say. People might want to pause it. Yeah, but don't. I think there's a lot to learn from others. I know. I mean, there's a lot of value of thinking by yourself, but the value of these communities is to also learn from others. I learned a lot looking at other people's solutions in competitive programming and on LeetCode. That's a great resource for learning. You always find better ways to do things, and I think it pays off to learn them. Okay, let me focus a little bit on this order. So okay, so we have the order. of the queries, and we also want to sort the rooms by size. How do we do this? Okay, let's rooms sort. So we don't need to keep the original order in the case of the so we want to sort by the size, which is the second component, and again decreasing order. Okay, so now we have everything sort. We are going to have another index for the rooms, J, and we want a result array of the length of the queries. Initially is none. We set all nonce, and now when we process the ith query, we want to make sure that we process all the rooms that have size greater than or equal to this query. Let's unpack this. So this is preferred, and this is mean size in the queries I. Okay, so while we have more rooms and the size of the room is greater than or equal to the mean size of the query, we are going to process it. So here we want to add it to the data structure that we're going to use. From sorted containers, import sorted list. Initially, our sorted list is going to be empty. How do we call this? Let's call this IDs. So here we want to, what is this, append or add? Add. So it's like set. So in this case, we want to add the room ID. Yes, that makes sense. And we increase J. Okay, so now we have all the rooms that are candidates for our query, and we want to do this. We want to find the preferred ID. I don't know how to spell preferred. Okay, there you go. Okay, and this is going to be our K index, which is going to give us the smallest element that is greater than or equal preferred. Okay, there could be none. In that case, it's going to give us the size of the IDs. I mean, the size of the sorted list. But we also want to, I think maybe we can do this. We can do a slice, because we also need to check the previous element in order, because that one could be closer to our preferred value. So we want this and we want this. This is the slice of the values that we care about, but there could be a problem because this could be negative and this could be I think if this is greater than n, then the size, it doesn't matter in Python, but here I think we need to adjust, because if we pass -1 is the last element in Python, so that could be a problem. So these are going to be our candidates. But we want the best for this query. So the best is another way. In this case, it's the minimum difference. So I guess we don't need this. We can just consider all those values, and this is a criteria. And the criteria is the absolute. We want to minimize the distance to preferred, but we want to break ties by the ID itself, the minimum ID itself. So that should give us the best value, but there is an edge case because this could be empty. And that only happens when the sorted list is empty. So that means that we need to add the default value, which is going to be -1. So this is our ID. I hate that ID is a reserved name in Python. And now we want to set the ID to the result, and we return the result. So I think this should work. So maybe I'm abusing this interface. Cannot specify a default for min with multiple positional arguments. Why not? Oh, so this has to be key. Okay, passes the examples. And it works. Great. First time. That was easy. Yes, I think this data structure is very useful. I think there's something similar in C++ with, I mean, it's an order statistic tree internally, and there is I mean, I don't think it's part of the standard library, but it is available in LeetCode, and you have this kind of operations. But I liked how we handled these edge cases. Without having to deal with them afterwards. We anticipated them. That's always good. It means that we've thought about this systematically. So Smart Coder, I thought about solving this without the sorted list using, I mean, you can do this with a segment tree, because you ask for an explanation of segment trees. But I don't know. I think it will end up being a little messy. I mean, you can solve this with a segment tree, but it will require... Totally forgot about that. Yeah, I don't. I take your requests seriously. So what was I saying? In order to use so the segment tree is it's like an array, but with some special properties. So with some, in this case, we only need to sum the values in a range. Yeah, no worries. So I think it's gonna be complicated. I mean, the code is gonna be long. I mean, we can do it. I don't know. I'm about to get my food delivered, and then we have the. I want to watch the Simon's stream, so maybe I'll leave it for tomorrow. But yeah, let me explain a little bit. So one thing that it will require is that here the room IDs, yes, I'm gonna post all of them, don't worry. I mean, it's set up automatically. So the room ID, this is kind of silly feature of the problem, because the room IDs can be large. They are all unique. But you can only have 10 to the 5 values. So this is a lie that there. I mean, you can do what's called index compression, and you just map them to indices. Like you map the smallest one to 0, the next one to 1, and so on, and you translate all the IDs into numbers from 0 to n-1, and that's going to guarantee that the values are bounded by this number. And therefore you could have an array that has a 1 when the number is a representation of a set. You have a 1 for the numbers in the indices of the values that are present in the set, and 0 otherwise. And then you can do binary searches to make this kind of operation, the bisect left operation, for a given value. And the segment tree gives you the operation of knowing how many values you have in the set that are less than or equal some position, some value, some given value. And that's how you can do binary searches to find this k, and then but I think you need another binary search to find the previous. So you find the next element and the previous element with a binary search each, and I think we could reuse the binary search code, but I guess if I had to do it in a contest, I would maybe copy paste it. So that's why I think the code is gonna be long, and I don't like it. Maybe I can find some other problem to use a segment tree. So yes, that is all for this problem. How long? So 25 minutes, but I think we solved it pretty quickly. So, okay. See you in the next one. Bye bye.